Imagine you've enrolled in a university course on digging holes. Like many others, the course had a prerequisite. In this case, the challenging class on tools for working with dirt. You spent a long semester learning to use all types of picks, trowels, and shovels, like this one on the left, and got an excellent grade. But at the first day of the hole digging class, the professor seems to expect students to be familiar with using an excavator, like this one on the right. Suddenly you're lost, and both you and your new professor suspect you've been inadequately prepared for the class. This perceived disconnect is how many engineering students can feel when transitioning from an important math prerequisite called differential equations to the engineering classes that depend on them. These differential equations are mathematical tools for understanding systems that are changing. They're used by engineers and scientists to model things like the fluctuating temperatures on a Falcon 9 rocket engine, or even the speed with which a virus is spreading. For a long time, methods taught in differential equations centered around paper and pencil solutions of equations that appeared in textbooks, but almost never in the real world. More recently, math educators have moved away from this one shovelful at a time approach by incorporating more realistic problems, focusing on conceptual understanding through problem-based learning, and incorporating the use of modern computing tools, the excavators of mathematics. But even with these ongoing changes to math instruction, engineering educators still find that students who encounter differential equations in engineering contexts have difficulty identifying which mathematical tools to use. More work must be done to help students effectively harness differential equations knowledge in problem-solving contexts. In order to accomplish this, we need to understand these students' ability to interpret their mathematical knowledge in those engineering problems. Yet, while most research is focused on increasing performance in differential equations classes, almost no one has investigated whether students are increasing their ability to select and apply these math skills in problem-solving contexts. This is a gap my research is trying to fill. This is important because research has shown that while mathematicians and engineers use many of the same tools, differences in their expectations, terminology, and even disciplinary values can prevent students from recognizing when and how to apply their math knowledge. And so, in conjunction with a series of cognitive task-based interviews and investigating the use of differential equations in current chemical and mechanical engineering courses, I'm investigating not only the views of the math instructors, but of the engineering instructors, as well as the very students who are constructing their skill set drawing from both areas. Only through this cooperation of areas of expertise can we understand how innovations in teaching differential equations can equip future engineers to choose the right tool for the job. Thank you.